Good afternoon, everybody. I'm Jessica Kerr, better known as Jessitron. I work for Outpace, and maybe, aw, this is not okay. And I'm here to talk about property-based testing for better code, as you will see in a moment. I want to talk about property-based testing because I learned a lot from it. Shit, I'm too... Okay, let's start this over. I'm going to talk about property-based... Oh no, that's its problem. Okay, we've talked a lot about failure at this conference, right? And we are going to learn from failure, and what we're going to learn is to take key point out of navigator mode. And I'm going to talk about property-based testing, which is also all about failure. And the whole point of this talk is not that I expect you all to go out and do property-based testing, because frankly, it's a pain in the butt. It's really hard. However, I did it, and I learned some stuff from it that makes my code better even when I'm not doing property-based testing. And the beauty of that is that when I tell you about this stuff, you can use it even without doing any property-based tests of your own. Thanks. Yeah. Oh, is this a clicker? Thank you. Okay, you guys are awesome. Definitions. Most of the tests we write these days are example-based tests, where we carefully consider what might be a representative input to our function that we're trying to test, and we pass that in, get the output, and see whether it matches exactly. With a property-based test, instead of that, we just randomly pick something that might be valid input and throw it in there and then try to determine whether that's correct programmatically without duplicating the code under test. That turns out to be really hard, often impossible. So instead, we just let's put a box around it and make sure it's pretty close to what we think the output should be. It goes up over here, it goes down over there. Close enough, we'll call that correct. And I just told you this was a lot harder, so why would we work way more hard to be less specific about our output? One surprising thing for me is that being less specific about my output gave me more freedom in my implementation. If I can make sure it meets the business requirements without hard coding exactly what it should be, that's given me a lot of freedom. So that's number one. But other than that, I'm going to have to do this presentation backwards in order for you to believe me. Because with property-based testing, it's a lot harder than example-based, and the small examples are just not motivating. So we have to start with something hard that doesn't work with example-based testing. Demo program today is about prisoner's dilemma. Prisoner's dilemma is interesting because it shows how cooperation can evolve even when the individual incentive is always to not cooperate, to bite the other person's back. The classic scenario is you've got two prisoners, they can't talk to each other. Instead, a police officer talks to each of them individually and tries to get them to rat out their partner. Each person individually does better if they rat out their partner, defect. But they both do better collectively if they both remain silent and cooperate. This is kind of boring in one round, but it gets interesting later. Before that, I want to switch from people to birds, because birds are prettier. And Richard Dawkins in The Selfish Gene did a great extrapolation of prisoner's dilemma. In his scenario, the birds have ticks, and they can pick off their own ticks except for the ones on the back of their heads. So they need their buddy to pick the tick off the back of their head. So here to cooperate, a bird picks the other bird's tick, and to defect, it flies off and leaves the other bird to bleed from the brain. There's 4 possibilities in one round of prisoner's dilemma. Either they cooperate and both pick the tick, or they defect and both fly off, or one of each. In order to simulate this and determine which bird is most evolutionarily fit based on its choices, scores are assigned to each of these scenarios. Both cooperating is best overall, but for any individual bird, defection is always going to get it more points. This gets really boring with one round because you'd have to be dumb to cooperate. But when you get a lot of rounds together, then it gets more interesting because each move is no longer only determining your score, it's also information to your partner. So now there's information transfer going on here. It's still useless if it's just two birds competing with each other because whichever one defects the most is going to win. Once you bring in more population of birds, and suddenly I'm not competing only with my partner in this game, but with a whole lot of other birds, it's to both of our advantage to continue cooperating with each other. This is when cooperation can evolve. We're going to simulate that. That's the goal, to simulate a population of birds in a forest, and they all want to play prisoner's dilemma with each other, and we're going to see which bird's strategy is the most fit for survival. We'll do this with the central coordinator, and it's very important that the birds not have any information other than their opponent's past moves. To do that, we must break the process boundary and put them in another computer somewhere, and let's say hypothetically the birds are accessed through HTTP and they're a service call that we make. So our central coordinator here is actually going to call out to the various birds to see what their moves are, and then tell the bird only the opponent's move to limit the information. How would we test this? Oh, and I forgot. How many turns is each bird going to get? Well, we don't want it to take forever if some of these calls are slow, and also it's important that the birds not know how many rounds are in the game, or else they'd always defect on the last one. So let's just set a time limit. We're going to have all the birds play furiously for however long we decide, and then we're going to cut it off, look at the score, and see which one won. How would we even test that? If we were going to write an example, well, okay, we can pick an arbitrary time limit, maybe 1 second. Pick the simplest bird, the one that always cooperates. You have to have 3 or it's not a population, so we'll keep that minimum. And then we can expect the output. Well, what's their score going to be? They should all be the same? No, because some might be slower than the other. I have no idea. I can't even predict this output. In this case, this asynchronous distributed system, there is no expected equals actual to check. It's not there. Instead, let's try to put a box around the actual output and see if we can fit it in there. So what can we say about this now? What statements could we make? One is, say, an invisible output here is how long that took to return. That's something we can make a statement about. The return time of this function is less than or equal to the time limit we passed in plus some fudge factor for overhead of calling it. Okay, this is a property. A property is something that's always true under specified circumstances. So after we've established a property, we can make logical deduction things from it and have confidence in it. In this case, what are those specified circumstances? Well, for any time limit. This should be true for any time limit. But that's not actually what we're going to test. So we will use a generator to produce possible time limits, and the generator here is going to produce things between 200 milliseconds and 1 second. The code here is Scala, and I'm using the ScalaCheck property test framework, but there's one for every language that's useful, so this is not specific to Scala at all. All right, so now we have a property, and I need to fill in the other variables here. One thing that I've started doing since I started property-based testing is to write my tests backwards, start with the assertion that I want to make. This works for all tests. So moving backwards, we need to fill in what is the return time. We'll put a timer around the game call. In order to play the game, we'll need the rules and some birds. So we can generate some rules and birds, but not just any rules and birds. We need to be specific about our input conditions. We want valid rules. with maximum, the rules here, by the way, are how many points you get for cooperating or defecting, et cetera. We need to make sure that we won't overflow max int in this case, and the number of birds are between 3 and what my computer can handle. One thing that's beautiful about this kind of testing is I'm able to specify my valid input completely, not just provide a few examples and expect people to interpolate between them, but completely say anything in this range, this is going to be true. And if I name my things carefully, instead of saying max equals 20, which is what that constant is defined as, I'm specifying why it's 20, because that's what I think my computer can handle, not because conceptually 21 wouldn't be okay. Now let's zoom in on this particular piece of specified input, the birds. How do I specify some birds? I said the goal is to put them over HTTP, but I'm not going to do that during a test. This is a functional test, not an integration test, and I want it to finish today after it does 100 runs with generated inputs. So what I'll do is I'll make ports and adapters. A port is an interface that my function accepts, and separately somewhere there will be an adapter that can make the HTTP calls to the birds. That's tested separately. What I'll do in my tests is provide some sort of test bird implementation that fits the port and simulates whatever it is I need to simulate in my tests that I might expect from an external bird. And in this case, that's more than just cooperation and defection. My test birds might cooperate, then they might be really slow and then defect. And then they might defect, and then they might throw a 500 server internal error. All of these things are things, I've used the internet. I know this happens. And you might say, oh, what a pain. This is so much work. I'd rather just assume that my birds are going to succeed. But the chances of that are not very high. So instead, I'm going to simulate a bird with a strategy. Strategy is one component, but the other thing is a sequence of instructions. I'll generate the sequence of instructions and put that in my bird so that not only will I detect failure cases, but I can reproduce the failure. Hypothetically, it's not completely reliable because this is asynchronous programming, but I can probably reproduce the failure cases because ScalaCheck will tell me what generated input triggered the failure case. So it's extra tricky to make an adapter for the bird that is predictably random. It's generated random, but once it's there, I know why it's there. So I've learned to use ports and adapters for external dependencies. I totally do this now all the time, and it's a beautiful way to draw lines among subsections of my application. It's been really good architecture. So now that I have these birds that can fail, and I have these little explosions going on in my test, and I did the math. If I've got 20 birds all playing against each other, and they make, I think it was 40 moves per game, and they have a 99.9% success rate, and I require all of those to succeed in order for my function to succeed, then my function will have a 20% success rate. So it's pretty important to handle that. And when, in my test, I expect failure and I create failure, I put it in there, and not just in the examples that pop to mind, but in all the examples that I could conceive to write into my generator. That makes me ask the hard questions of what do I do in this case? I have to push back on, maybe it's our architecture people, maybe it's the business, maybe it's just me. I have to think really hard of what do we do when a bird fails? Is it disqualified? Do we drop that game from the scoring? I don't know. I do know that the answer is not, my function blows up. My function returns in the specified amount of time. So now we've got a property-based test with some specified and simulated with failure and everything input, and we're quite certain that this is going to return within that time limit. And it runs 100 times on our machines, we push it, it goes to CI. Every time our build runs, we get more and more confident about this property. But this isn't a very interesting property. It does not tell us that the output is correct. In fact, it completely ignores the output. So the next thing I do after I make this pass is to add the output in and determine whether it's acceptable. I want to put a box around that. What is that box? What is an each on each result? Well, I don't know yet. I haven't defined it. Start with the test. I know that the business wants to know which bird was the most fit. So maybe they're going to get a map of players' birds to scores. But that's not enough for me to tell whether the function worked. I don't even know how many turns each bird took. But I could return that. If my function returns both the score and the number of turns, then I can put that in a box. I can say, well, the maximum possible score was this, based on the rules, and the minimum was this, so is it at least in there? Maybe I want to verify that every bird played against every bird. So then my function could return a list of the games that were played. If I want to get really specific and make sure my scores are completely correct, I could return a list of moves that were made in each of those matches. Now I have everything necessary to determine whether this result is correct. I can put it in a pretty darn good box. That was driven by what I needed for my properties. Output all the useful things. This is something that I started doing because property-based testing, and it's been incredibly useful since, for two reasons. One is, on the business side, right now I'm outputting some result and a bunch of context. If the business accepts this, I can give it all back to them, and they can use this, for one, to see why my software generated the result that they're seeing, and they'll have a lot more confidence in that result. And for two, they can look at that, do some reasoning, and come up with ways to improve the software based on a result with context. That's valuable. The other thing this gives me is visibility into the working of my function. Because if this is the data that I need to determine whether it's working in test, this is also the data that I need to determine whether it's working in production. This is what I would print to a log, either occasionally or all the time or on request. This is how I can be confident that my software is working. Adding this extra visibility is a lot of work, and it's completely essential. This is how we learn. This is how we make our code better over time, by being able to see what it's doing without attaching a debugger or anything silly like that. So now we have some generated input, and we have some properties of the output. We've drawn our boxes around this function, and we've generated a bunch of input, and it fits into the boxes, except when it doesn't. So what happens when a test does fail in continuous integration 4 days after I committed this code because it finally found some bizarre corner case that it had never tested before? First of all, I'm distracted and very frustrated. But I remember this is a learning opportunity. In Avdi's presentation yesterday, he said, experiment and fail, and that's how we learn. Experiment, fail, and ask why. And that's how we learn. So here's our random generator monkeys did our experimenting for us, and they found a failure for us, and it's our job to ask why. And in my experience, 90% of the time, this is not a bug in the software, this is a bug in the test. And some people resent that, but I don't. Because every time I fix the test, I'm also fixing my mental model. I am learning something about this code. And over time, as we find more of these, my code gets better, my mental model gets better, my tests get better. I love maintenance. I'm serious. But the first thing I do when it fails is not fix it. The first thing I do when it fails is get the test to tell me why it failed. There's a lot of adornments that I can put on any test, including a property-based test. So when it fails and it prints out some gobbledygook that I can't understand, I will go make that understandable before I fix the test. I'll take whatever input generated input happened in production, hard code that into an example test so I can reproduce it and run it over and over. And then I'll start adding toStrings to my properties, labels, and toStrings to the generated, like the test bird kind of thing. Maybe I'll make the name pronounceable. I'll add labels. I'll have it print out the intermediate steps that I need to find out. And then shrinkers. Who was in Zishan's talk yesterday? Hopefully most of you, either you weren't there or you're just lazy. He talked a bunch about shrinkers and when he's generating data in Clojure. And they're really cool because when a failure happens, then the property checking framework will start taking those inputs and making them smaller and smaller and smaller to find the simplest possible input that will cause the failure. That helps me know why it failed so I can learn something. I think of example-based tests as anecdotes, as stories. These are really easy for people to think about, to come up with, to talk about. We think they're easy to read, at least when we're writing them, although I never come back to an example-based test and say, oh, look at that. Stories are easier for us, while property-based tests try to create evidence of something. In science, the question is, what do we know and how do we know it? Property-based tests are very specific about that. Example-based tests ask for interpolation. Humans are really good at interpolation. Computers are lousy. So I want to go to another property that's much simpler. Let's look at the properties of the rules. Now we're like backwards, we're on the track toward the simpler things. The rules have 4 attributes: the reward for mutual cooperation, the penalty for mutual defection, the temptation to defect, and the sucker's penalty. So these four integers make up rules. And I can say stuff about those. I've got a score method that takes some rules and a set of moves, cooperate, cooperate, or cooperate, defect, and outputs the points, a pair of points corresponding to each move. I could make example-based tests for this, which would be, well, the rules have 5, 4, 3, 2, and so cooperate, cooperate gets 3, 3. And I would totally be duplicating the code, because that's exactly what the rules do inside. Instead, I can say something. I can make a statement about the rules. Prisoner's dilemma means defection is always better for me, and the best global outcome is cooperate. That defines the business concept here. Also, the game is fair. If I swap the players, their scores swap too. That's a nice property that lets me just then ignore the order of the players everywhere else. I'm going to zoom in on one of these. Defection is always better for me. When I write this one, my goal is to say, well, for any set of rules, and for any move my opponent might make, it's better for me if I defect than if I cooperate. Strictly better, not equal. I can fill that in by calling my score method twice. I hold their move constant, I vary my move, and then I compare the output. This is a relational property because it runs the function under test twice and compares the output. It's a really good way to put a box around things without specifying them precisely, but instead specifying them in a meaningful way. This is also an incomplete property because the output's not fully specified. I would like to show you a complete property as well. So for this example, meet tit for tat. This is the bird strategy that usually wins in prisoner's dilemma simulations. In tit for tat, the bird cooperates at first and then just does whatever his opponent did last. You defect, I defect. I can make a complete specification for this bird's test. What I want to say is tit for tat starts with cooperate, then copies the opponent. So I say that his first move is cooperate, and his other moves match the opponent's moves, time shifted by 1, the prior moves. I can fill that out. They play a game for an arbitrary number of turns against an arbitrary opponent. I can get my first move and all my subsequent moves, and then I can take the opponent's moves, time shifted by 1, and make sure they're identical. This is a complete specification of the tit for tat bird. Pop in a couple generators, and I'm done. This one was actually not hard to write. What's beautiful about it is it says why that output is correct. Compare it to an example. If I wrote an example for tit for tat, I might hard code some opponent moves, play the bird against it, and then verify that my moves match some hard-coded expected value. That says nothing about why the bird did that or what meaning it has. A couple other little perks of easy-peasy properties that you should totally do this. If you're writing serialization, deserialization, great time to generate the object, serialize it, deserialize it, make sure it's the same. Easy peasy. It won't catch matching bugs, but it'll catch other ones. I kind of use that sometimes. If it's hard to generate the input and then formulate the output without duplicating the code, I'll generate the output, decide what input should produce that, and then sort of go backwards and make sure those are the same. That's just a couple tricks that makes writing properties easier. Next, I want to talk about generators. Now, we're getting into something a little specific to Scala, and those of you who were in Zishan's talk yesterday can contrast this with what he talks about in closures. Generators are how we produce any sort of valid input and how we specify what valid input is. In ScalaCheck, a generator of type T is basically a box with a button, a method, that you push the button and it outputs something of type T in a box. Except when it doesn't, sometimes it gives you an empty box. Scala. It's an option, really. And then you push the button again, and you eventually get something of type T and use it in your test. Let's look at the generator, the custom generator that I wrote for rules. There's a whole slew of built-in generators for given types, but here I want to be really specific about what is a set of rules. I've got those 4 numbers there, and they have relationships. Somewhere between 0 and the max number of points are these 4 numbers. Within that, they can move around as long as they maintain these relationships to each other. I can build that up out of the built-in generator choose, which just gives me an integer in an inclusive range. So I can find the t, and then the r is less than that, and the p is less than that, and so on. And one more thing, I want to specify that cooperation is best. So I put a guard clause here that says 2 cooperating birds do better than 1 defecting and 1 cooperating. That's a guard clause, so if it is not passed, if that condition is not met, that's when I get the empty box. That's how ScalaCheck composes generators in the Scala syntax. There's another thing that's specific to Scala and actually really cool, and that is, once I make this rule generator, I can make one of these and make it available to everyone. If I take that rule generator and pick a value for the maximum, and I use that keyword implicit, then I put it in Scala's magic hat for anyone to use. The first thing I learned when I did this was that my defection property failed because, as it turned out, once I dug into why it failed in the simplest possible test case, it was hitting integer overflows when it added the scores together. So I changed this to max value over 2, and now it works in a lot of places. That implicit keyword there tells Scala to take this thing and put it in the magic hat. So Scala has a magic hat for implicits. And then later, whenever any of my tests needs to use rules, they can get them out of the magic hat for free. That's just totally convenient. I don't have to specify a specific rule generator unless I want to. The other thing about these generators is that I use them in the tests that I wanted to use them in. I use them in the other property-based tests. I use them in example-based tests when I just need a valid one of these things to pass in, you darn type system. And I can pass that in and not be too specific about it. And it becomes so much easier to write tests at a wider level because I've got these generators that'll just hand me valid things all day. They're super useful for that. We can build them up as well. When I have a generator for a strategy and a generator for a name, I can put those together to get a generator for a player. And then if I put that one in the magic hat, there's a bunch of other stuff in the magic hat for like general types, including sequences and tuples and maps. And so, poof, I get a generator for a sequence of players. I could also have for free a generator of maps, of strings to players, et cetera, et cetera, et cetera. That's just kind of a cool Scala trick. In a closure in other languages, you'd probably have to specify how to build that, but it would be one line. And then you add some rules, and then you can get a generator for game. You build up from small to large. This enables me to write tests at a higher level, which is really important. And it's totally worth the time. I'm not big on reuse, but one thing I've observed is that these generators are more reusable than any production code I've ever written. And back to the part where they let us build up bigger tests. If this is your subsystem, and these are the little classes inside it, this is your web service or your each on each game, whatever external API you have is this outer ring, and these are your classes or your units of abstractions into it. The way I learned to do unit testing, You'd want to start with a test. Well, it's really hard to write a test for that big thing. Its interface is long. It's much easier to write tests for the small things. And I was told that a unit test is the smallest possible scope, like one method on one class. I was taught wrong, okay? Not just example-based tests. That's just, frankly, the wrong way to unit test, because it puts each class in a cage, and I feel like every example-based test is a bar in that cage, because anytime I want to change it, I run up against that test, and it's got hard-coded expected equals actual, and I don't even know why, and I don't want to know why. I just want it to go away and let me change my code. And each one is in solitary confinement when it's surrounded by a bunch of tests that are specific to that class. Plus, these are crappy tests. I mean, individually they may be fine, and if you use them to drive your design, totally fine. Drive your design and then delete them. Because right now, this is not helping me refactor. Each class is in its little box and it can only move this far. What helps me refactor is if I hold the outside API steady so that I can change the insides without messing up the outside. I want to test the API, test the external facing stuff. So I can put them all in one big cage. That would be a big improvement. That tests the seams between the inner classes, and that's where the bugs are. The bugs are hardly ever within a class. They're between the classes, right? So this is a much better test. But doing this example-based is a lot of work. Look at all those bars. I got bored just drawing those. I don't even want to spend that much time typing or coming up with all the possible circumstances. So I want the generated circumstances that make this easier. Generators make this easier by building up from smaller parts and by putting together all those combinations that you don't want to think of. And then the output part in properties makes more sense at this level too, because when you hard code the output of something this big, oh my gosh, you get like JSON that's like this, and that doesn't help anybody. And then you change the functionality of your service, and so of course your test fails. It's supposed to. You changed it, and then what do? You take the new output and you cut and paste it into the test, because what are you supposed to do? Specifying relationships gives that a lot more meaning. So the goal then would be to put the whole thing in one big orange box and specify the properties well enough that the business is satisfied, that all the customers, the callers of this service, can count on it, and then I can move around my classes inside. Now, realistically, this isn't black and white. This is a spectrum. I might have some more tests of smaller classes, like of the rules. I might have a few bars in my cage. For instance, if I'm adding a column to a report, and there's a property-based test maybe, and there's also a test that has sample input, sample output. That test is documentation. It's helping people who land in this code base and want to know, what does this report even look like? I can totally add the column in there. I'm fine with that. There's a whole spectrum in here, and example-based tests sometimes make good documentation. This isn't all or nothing. Another way to think about it is example-based tests are very narrow on their input and very broad in their expectations when they're hard coding expected equals actual. A few days ago, I added a column to a report, and I had a little test that tested that the column was there, and that was happy, but then what test broke? The test that said whether the rows were sorted, because it had hard coded expected equals actual, and its expected didn't have this new row in it. I don't care about that row in the sort test. So what I can do there is sort of narrow the output specifications and say, instead of saying expected is actually equal to this, say, does expected have the property that I want? I can ignore all the fields except the sort columns in my sort test, and it will be a better test, and it will be a much looser cage. That's a big plus. Of course, the extreme to this is property-based testing is all the input in the world and the minimum specifications on the output, leaving as much up to my implementation as I can. And then we get the classes moving around, so my code can improve over time. As I learn from all the beautiful visibility that I have into what it's doing, I can make it better. All of that comes down to defining success, I think, to thinking really hard about what it means for this service to be correct, what it means for this service to fulfill the expectations that users have of it. This is really hard. When I do property-based testing, test first, I wind up sitting there in my chair, lollygagging around for about 2 hours before I could even write part of a test. But this gives me an understanding of the problem. We don't choose this because it's easy. We choose it because it's hard. More thinking, less typing. Define success, and then go looking for failure. The closure community calls this hammock time. Hammock time is when you sit back and think about the problem before you try to solve it. And it's a really good idea. What I love about property-based testing is it combines hammock time with monkeys, with randomness. You take all that careful thought, and then you combine it with chaos. And you get confidence out of this. Functional programmers love to talk about reasoning about code. They're actually totally right at a small scale. Understanding some logical reasoning system is essential to being a careful programmer. But don't tell me I said this. Deductive reasoning doesn't scale. It only goes around what we can fit in our heads, which is frankly tiny. Trial and error totally scales. Trial and error is how we got here. It's how evolution works. Property-based testing takes that trial and error, those monkeys, and turns it into statements that we can reason about. It turns it into properties that we can use for deductive reasonings. I know this game is fair, therefore, it doesn't matter if I swap the order of the players. That's really cool. I love that about it, especially when you've got an asynchronous distributed systems. There's really not any other way of being sure about something than to try it a heck of a lot. I know you wanted to see all of these brown circles on one slide, but they didn't fit, so you just get my favorite ones and a monkey. There he is. I was thinking about this today in relation to the keynote yesterday morning. I hope you were all there. That was amazing. And one thing Jeff Norris said was that advice that Alexander Graham Bell's father gave him about one small bird in the hand is better than a score of birds with their tails unsalted. A score of large ones with their tails unsalted. That's what it was. And of course, that was terrible advice for Alexander Graham Bell because it was incredibly limiting. And I kind of feel like our little example-based tests that are easy to come up with, and we're comfortable with them because they're stories, and the business people can specify in their requirements documents exactly what the output should be. Those are like those small birds in our hands. And sitting back and thinking about our code and coming up with properties that are always true that we can later use for deduction, that's more like the large birds with unsalted tails. So let go of the small birds that are keeping you caged in and chase the large birds with unsalted tails. What's the worst that can happen? You get lower sodium intake. I'm Jessitron. The code is up here, but don't check that out today. I actually totally screwed it up last night. Give it about a week, and then it'll be really useful if you want Scala. My favorite book on property-based testing is ScalaCheck. It's about, short book, it's about half specific to ScalaCheck and about half property-based testing in general. It's where I got my start, and it's pretty good. Any questions? We have at least a minute and a half. Nobody ever asked me any questions. Thank you, everybody.